So as you can see on the shared window, today we want to talk about quadratic polynomials. Okay, we already studied and talked about quadratic equations. We learned how to solve them. Now we want to discuss about a quadratic polynomial, quadratic polynomials in general. So what do I mean by quadratic polynomial? So if you have a function f of x which has this general form that ax squared plus b of x, p times x plus c, in which a, b, and c are all real numbers, and of course a is not equal to 0. Yes, this is called a quadratic polynomial. So please differentiate between the quadratic polynomial and quadratic equation. Yes, so here I do not have any equation. I'm not looking for finding x at all. Might be there are some connections between those we studied, those material we studied for quadratic equations and the one which we will study for quadratic functions, but I want you to know that they are two different things. Here I am not solving anything, I'm not looking for x, I am just looking this as a function. And the reason, of course, again as before, that I do not assume that a is equal to 0, because if a is equal to 0 then this is gone, then I will get a first degree polynomial, and first degree polynomials, as we will study again, are just straight lines. So in a straight line, not, of course that's also something that we need to study and reveal in the next chapter, but usually you are a little bit familiar with the straight lines from your previous studies. But here we want to talk a little bit about the structure and the behavior and the properties of a quadratic polynomial in general. Okay? So this is, let me just write it here, so that is called a quadratic polynomial. Polynomial, or if you want to, you can say a quadratic function. Okay, so let me change my color here so to emphasize that here ax squared plus bx plus c equals to 0. This is not a quadratic polynomial. You can say this is a quadratic polynomial equal to 0, but this is called a quadratic equation. Okay, so be careful about these difference between these two. Okay, so for example, I cannot ask you to draw the graph of a quadratic equation. I can ask you to draw the graph of the quadratic polynomial. I cannot ask you to solve a quadratic polynomial, but I can ask you to solve a quadratic equation. So these are the main differences. Yes, so please appreciate these differences. Okay, if I ask you what is probably the simplest possible quadratic equation ever, what do you answer? The simplest possible quadratic function, quadratic polynomial.
If b and c are equal to 0?
Exactly. Because a cannot be equal to 0, otherwise I will not have a quadratic function in the first place. But if I want to make it as simple as possible, I make b and c equal to 0. And what is your choice for a if you want to make it very simple?
1 probably.
Yeah, probably the best option is 1. Okay, so let us investigate a little bit about this very fundamental quadratic polynomial. So what, more or less, I am claiming that there are two fundamental, let me call them P and Q, it's easier. Polynomials usually are denoted by P and Q. So let me consider this function, and then the other one, which is also very simple, but slightly different, I would choose minus 1 for a, and I would write minus x squared. Yes? So these are probably the simplest possible quadratic polynomials. What is very interesting is that the main properties, the general aspects of these two functions will be inherited to any other quadratic polynomials, even though they are a little bit more complicated. Yes? So this is very interesting. The geometry of these the graph of these simple quadratic polynomials will be inherited more or less to the general cases. So let us investigate a little bit about the graph of this function. For example, I can ask you some of these questions. For example, I can ask you, what is the minimum value, if there is any, that p of x can attain? What does it mean? It means that I do not have any limitations for my values of x. I can choose whatever x I want to. There is no limitation. There is no fraction that I need to be worried about. The denominator cannot be 0. There is no square root sign that I need to be worried about. Under the square root sign cannot be negative. This is just x squared. Whatever I put instead of x, I can immediately calculate x squared. What I just described means that the domain of this function is actually the set of all real numbers. Any number that I want to, I can put in. So I have infinitely many possibilities for x. For each one of those values that I put in as x, I will get an output. For example, if I put 1 here, so if I put x equal to 1, p of 1 becomes equal to 1. If I put x equal to square root of 2, the output that I get would be square root of 2 to power 2 is 2. So for this input, my output is 2. For this input, my output is 2. Now assume that, of course, this is not practically possible. How many choices I have? Infinitely many. But assume that you start feeding all these infinitely many to the function, and you get actually infinitely many values out there. Practically it is not possible. But can you argue what is the minimum number in this infinitely long list? Based on an argument, not based on calculation. Calculation is not possible because there are infinitely many possibilities. Can you predict what would be, for example, the minimum value that you will get as the set of your outputs at the end, even though doing it practically is impossible because we have infinitely many of them?
0 if x is 0.
Yeah, can you defend your argument?
That's because if you multiply, say for example, you take 1 to the power of 2, then you still get 1, but 0 is lower than 1.
Yes.
And if you take any other number to the power of 2, you get a number higher than 1.
Yes.
And itself.
Yeah, so exactly, more or less I would agree with you. So you were, first of all, is 0 achievable? You would say yes, because we know that if I calculate p at this particular number 0, this becomes 0 to power 2, this becomes equal to 0. So it means that in this bag of values, assume that this is the bag of your values here, definitely you will get some number here which is 0. Okay, why? Because I put 0 here, I got 0, so 0 is one of the outputs that I get. But according to Benjamin, we want to claim that, of course, I will get infinitely many outputs in this bag, but we are claiming that all of them are higher than 0. And the answer is clear. Why? Because if I don't put any number which is not, if I put a number which is not equal to 0 here, then if x is not equal to 0, do you agree that x to the power of 2 is definitely a positive number? Yes? Even if x is negative. Even if x is negative, because I am raising it to an even power, x to the power of 2 is definitely positive. So you are saying that if x is not equal to 0, x squared, which is my output, is greater than 0, this number. And for this particular number, I get 0. So it means that any other point that you see in this bag has a value greater than 0, and 0 is in my bag as well. So what does it mean? It means that 0 is the minimum value of my function. Okay? If you have any questions, please interrupt me. Okay, now let me ask you, if you look into your bag of outputs, do you see that, can you tell me what is the maximum number that you see in your bag here?
So that infinite, I mean, there's infinitely many big numbers.
Exactly, so you are right. So you cannot point into one single number. You would say there is no maximum for this function. Because when you say there is a maximum, it means in principle you should point to a number and say, yes, this is the maximum in my bag. But it doesn't matter. Is 1000 your maximum? No. What doesn't do you think that 1000, let me write it, 10,000. Do you think 10,000 appears in the bag? Yes. When I put x equal to 100, it will produce this number in my bag. So 10,000 is in my bag, but definitely 10,000 is not the highest value here, because if I choose x equal to 101, for example, and I square it, definitely it becomes a number which is bigger than 10,000. So this tells you that 10,000 is not the maximum value. Okay, so forget about 10,000. Is 1 million the highest value? We would say no, because if you, first of all, is 1 million in the bag? Yes, because if I choose 1000 for my input, the output would be 1 million. And is this the maximum value? No, because it is enough to choose 1001 and square it. It becomes a bigger number, which is in my bag. So hopefully you understand that it is pointless. There is no biggest value, there is no maximum in the bag, even though there is a minimum in the bag, and that is equal to 0. Okay, so this is for this function. Yes, so minimum of p is equal to 0, maximum of p does not exist. Okay, now let us do some bag for this function now. What do you think would be the situation there? For function q of x this time.
So it's the negative of a square of a number.
Okay, so for example, if I want to answer the same questions for q of x, minimum of q, maximum of q. Okay, so I want to answer the same question for this function. What do you think? How do you think about this problem now?
It's just the opposite of the first one. You can't have a minimum because the lowest negative number is undefined.
Yes.
And the maximum is 0 because...
Yeah, the maximum is exactly. Thank you very much, Benjamin. So this is the one. So here you would say it does not exist. And then you say that this maximum is equal to 0. Okay. Why maximum is equal to 0? First of all, I need to show that 0 is indeed in my bag. Yes, 0 is in my bag. Why? Because if I calculate q for the point 0, I get minus 0 to power 2, which is again 0. So this output 0 is achievable, and it is achieved when x is equal to 0. So yes, 0 is a point in my bag. But then here, all other numbers that you see in this bag share a common property. All of them are positive. So 0 is here. All other infinitely many numbers that you see in this bag are all positive. But I hope that you agree with me this time that all numbers except this 0 are all negative numbers, yes? Because after squaring, of course I get I have a positive number, but because of this extra minus sign, every number which were positive now turns into a negative, yes? So I would say that every number that you see here is now a negative number. So this means that the highest value in this bag is 0. So you see, that's a very powerful argument. Without checking all infinitely many possibilities, which was not possible in the first place, I was able to convince hopefully you that in this bag 0 is the highest value and in this bag 0 is the lowest value. And they are achieved both at 0. Okay? So what was crucial here? Can you tell me what was the crucial point which makes this one to have a maximum and this one to have a minimum? So sorry, the other way around. This one has a minimum, this one has a maximum. What was crucial? What was the crucial difference between these two? There is only one difference that you can immediately see. What is that?
One is on the positive side, and the other is on the negative side.
So I would say this sign is crucial. Yes. Here I have a positive sign which I didn't write, and here I have a negative sign I didn't write. And it turns out that this is actually indeed the case. The sign of the quadratic term is crucial to understand the behavior of this function from max and minimum points of view. You will see that this is the case if a is positive, then this function will not have any maximum, it will have a minimum. And if this number that you start with is a negative number, then this function doesn't have any maximum, it doesn't have any minimum, it has a maximum. So this is a one symbol property that will be inherited to this. Okay. Okay, and then let us go, for example, here to this one. Let me just clean this and then try to a little bit see that in practice what will happen. So y equals to x to the 2. Yes. Oops, it's not the right thing. So y is equal to x to the 2. So this is the graph of your x squared. And you see that the graph of the function, the height of points, by the way, the height of points are the outputs. When you go horizontally, these are the inputs, these are the x coordinates. When you go up and down, you are changing your outputs. So you see that all the outputs are non-negative, and this point at 0 is the lowest, has the lowest height, which is equal to 0. All other points that you can see here are actually higher than 0. Okay, let me also draw the graph of minus x to the power of 2 as well. So I don't know why GeoGebra doesn't change the colors, and so let me myself change it to the green. Okay, so I don't know, might have just changed the adjustments a little bit. So this is y equals to x squared, and then this is equal, sorry, this red one is minus x squared, and this black one is y is equal to x squared. Okay, so whenever we go below the x-axis, it means the y value is taking a negative value. And when we go above the x-axis, it means that the y value is going to take a positive value. When we go to the right, x value takes a positive value. And now when we go to the left, x takes a negative value. Okay, let us now go back and try to see how we can come up with this. By the way, this is not a straight line, you see. And there is a name for this type of graphs, okay? But it is a little bit more advanced. I want to tell you the name. The name is a parabola, yes? So these kind of shapes in mathematics are called parabolas. But of course, parabola, if you want to understand, so if this is not the case that every curve like that is a parabola, yes? So this is not the situation like circles, yes? This is even for circles that is also possible. So there is no guarantee that when you see something is very, very similar to a circle, you say that this is a circle. In principle, it might happen that the radius from one point to the other point deviates a little bit so that you cannot detect it with your eyes. So it is not a complete circle, but you think that's a circle. So I mean that even for the circle case, there is no guarantee that what you see and you say this is a circle is a circle. But of course, the geometry of a circle is much simpler. How should I understand that this is a circle or not? I need to be able to measure the distance from the radius center to the perimeter of the circle for any point on the perimeter and see that all of them are the same numbers. If you want to understand such a thing for a parabola, it seems much more complicated. In a later lesson, if we have time, I will talk a little bit about geometric properties of parabolas. But at least you have a feeling that this is a parabola. For example, if I just take these two away and I just write y equals to x to the 4, you will get this one. It is more or less similar to what we had before, but you are not allowed to call this parabola. Okay, so there is a reason why we call those shapes parabolas, but it is a little bit more advanced. I don't want to spend time on it right now. Okay, so this is also something it's good to know. Now let us go back and discover about, so let me clean this one and then go back, for example, here. Let us go to our analysis here. Here, let us try to understand a little bit about the graph of these functions. Yes, so what can I do? For example, do you have any suggestions? If you just want to do something naively, not very sophisticated, and you want to find a clue about the general shape of the graph of this function, what do you suggest?
Are you talking about quadratic polynomials?
Yeah, for example, I'm just talking about this very single one.
Oh, for just x squared.
Yes, exactly. So what is your suggestions? If you just, I don't want you to do something sophisticated. Yes, so I just want you to do a very simple thing to get an idea what would be the shape of the graph of this function. What do you do usually?
Well, one thing you could come up with is that you know that there will be like, I don't know how to explain it, but like a matching point on the positive and negative side, since you square it.
No, before, yeah, you are right. No, you are completely right. But before going to that step, so how did you come up with that? I think might be you are saying that I will set up a table of values and try to find some points on the graph and hope for the best that using those points I can have a clue about the general shape of my graph. Yes?
Yeah, I have an idea, Babak.
Yes, yes, I'm hearing.
You determine whether the answer is positive or negative.
No, but do you understand what I mean? Let us go back to the previous picture here. If I ask you how many points are on this graph, of course there are infinitely many points. But if I want to get an idea about the general shape of the graph, I would say that for every graph, not just quadratic functions, the one thing is that comes to mind is just to set up a table of values. For example, I will do this thing for this function. I will put x here, and then I put y here, which is x squared in this case. And then, for example, let us put 0 here. And what is the y value for 0? It is 0. For example, let me put minus 1 here. And then the answer would be positive 1. If I put minus 2 here, the answer would be positive 4. That is, I think, what is Rocco was suggesting. So if I go 1, this becomes 1. Then if I put 2, it becomes 4. Of course, the problem is that how many points is it enough to say, okay, I found this? If you don't know mathematics, then it in principle, it is not enough. You stop. You have to continue until forever, which is not practical. Why? Because even if you find 3 points and then you stop, okay, because then you can say that one possibility is to draw the graph like this. One possibility is to draw the graph like this. One possibility is to draw the graph like this. Yes, how should I know? So you see that by 3 points, all of them are passing through those points. But which one is the real one? And it turns out that it doesn't matter. You cannot answer on unless you know the higher mathematics. So it is not that trivial thing to draw the graph of a function just by some points. Yes. So you might say that, okay, if I have 3 points, I want to say to you that this is not possible. One way to do that is to consider this point and see that, okay, you see this is another point. By checking another point, you see that, okay, the graph cannot go like that. Then of course you might say that the graph will go like that. But even from here, I can do it randomly. How should I know which one is the real graph? So the point is that I hope that I can convince you that it doesn't matter if you determine thousands of points on the graph, there is not still a guarantee that the graph, how the graph looks like. Definitely these are the points on the graph. But it depends very much to the behavior of the function. If the function is a well-behaved function, mathematicians say a well-behaved function, a polite function, a continuous function without sharp points, these are called polite functions somehow, then you say that, okay, I can connect them smoothly and hope that I will get a shape that is very close to the real graph. But how should I know that the graph is a polite graph, the function is a polite function and behaves politely? This needs mathematics. Okay? So there is no guarantee for you. Might be, of course, you saw the graph of the function. By looking at the graph of the function, you realize that x squared is a polite function, is a well-behaved function. But remember, the logic is the other way around. The logic is to draw the graph with using the formula for the function, not the other way around. Okay? So these are the concepts that you will start learning by going to higher mathematics. But I want you to understand that if I do not have a mathematical tool in my hand so that I can say something about the graph of the function, it doesn't matter how many points I check, there is still a chance that my function doesn't behave very well in between the points. So these are the things that you will learn in the next lesson. But hopefully you don't need to be worried about this, because at this level of your lesson, or at least these polynomial functions are well among the well-behaved functions. They are categorized as well-behaved functions.
I have a question.
Yes, please.
You said earlier that all other quadratic polynomials inherited some traits from these two that you've shown.
Yes.
Is that true for higher level polynomials as well?
No, they are not. So if I go to x to the 3, you mean you mean about the no, the x to the 3 functions are more complicated a little bit. The diversity of the graphs that you might come up with are different. So here you will see at the end of the day, these graphs that I drew here for you are the typical ones. So all of the functions that you will see, that if they are quadratic, they will be of this form. So it means that either they are of this form or they are of this form. And that's a general feature. The only difference is that here I started from the origin. For different functions, you might start from somewhere else, higher or lower. You see, all of them have this type or the other way around. So that is the nice thing that we want to come up with without memorizing it that much. Okay, you have to trust me at some point, but I want to try to make it clear for you that this is going to be the case for other ones. Okay, so if I want to do this, I would draw a graph like this. For example, I will set up a coordinate system here, and then what I do is this. I would say that, okay, this is my x-axis and this is my y-axis, and then let us go here. For example, point 0 and 0 is just this point. So let me, by the way, change the color. So this point 0 and 0 is one of the points. And then what I have point 1 and minus 1. So let me take this one to be 1 and this point. So I am taking this one to be 1. Okay, so to make it a little bit more transparent. And then definitely when I put minus 1, I also get 1, you see. So let me just take that. Yeah, this is another dot, yes. What are the coordinates of this point? It's 1 and 1, so this is 1 and 1. And this one is minus 1 and 1, so this is this point. And then if I go to 2 and 4, so 2 is here, and this is 1, this is 2, this is 3, this is 4, so this becomes here, yes. That's that point. So that is that point, so I forgot 1, 2, 3, 4, it's here, yes, am I right? Yes, so that is another point. And then another point is minus 2 and 4. Is exactly what Rocco was actually mentioning here. So let me just say this is 2 here. And then I will have minus 2 here. And then I will go up here. Okay, so now what is happening? Is this behavior predictable for you? So you see, the reason it is not clear that this graph, but based on the fact that I guarantee you that this is a well-behaved function, so you don't need to be worried about the odd behaviors in between. This will go smoothly, okay? You need to trust me on that. And this is not that sharp. It should be very smoothly here. Okay. So now, can you tell me, is this behavior of being symmetric predictable for you? My graph is not a very good one, so let us go to the real one and take this one away. Can you feel the symmetry here?
Yes.
Yes? What is on the right-hand side is exactly on the left-hand side. So this portion is repeating itself as if the left-hand side is the mirror image of the right-hand side, or the other way around. Okay, so can you detect which property gives rise to this fact that this, so I mean, was it predictable for you that this should be symmetric? How by looking at this table you can predict this behavior of being symmetric with respect to the y-axis?
You can see that minus 1 and 1.
Yes?
Like 1 and 1.
Exactly, yes. That is important. You see, you have two opposite numbers on the x-axis. What does it mean? It means that I have 1, I have minus 1. But if the value of 1 was here, the value of minus 1 was somewhere else here, then they are not symmetric, because these 2 points would be the same. They are not symmetric with respect to the y-axis. But you see that this does not happen, yes? This does not happen. By changing x to minus x, the values are repeating themselves. And that is also clear for here, yes? I am changing, by changing x to the negative x squared does not change. Why? Because negative x squared to power 2 and x squared to power 2 are exactly the same. So even though I am changing the value of x, but I will go to the same height. Yes, because they have the same values. So if I choose 1 and I go to height 1, this is the same that if I choose minus 1, I will also go to the same height. So the final points are symmetric with respect to the y-axis. Okay, so for example, let me just test your understanding a little bit, even though this is not exactly your lesson, what I'm telling you now. For what do you think about this? Do you think this function, even though not polynomial, is this symmetric with respect to the x-axis, to the y-axis, or not?
Yes, all polynomials like that with an even exponent should be symmetrical.
Yes, exactly. Yes. So it means that they remain the same. The value of y remains the same if I change x to minus x. Okay. So for example, let me talk about this a little bit stranger function. X to the 4 plus 2x squared plus 1. What do you guess about the behavior of this function from symmetry point of view? We don't know the graph. Even I don't know what the graph is. But let us draw the graph. What is your prediction? Do you think that this graph is symmetric with respect to the y-axis?
No.
I think it is, but I can't really explain.
No, you can. Benjamin, are you talking? You? That is you, yes?
Yeah.
Okay, why you cannot explain? I just told you, everyone. So just think a little bit. Your guess is correct. This is symmetric. Why it is symmetric with respect to the y-axis? Because, anyone else? This is symmetric with respect to the y-axis because if I change x to minus x, let us see what happens. Wherever you see x, put minus x. It becomes minus x to the 4 plus 2 minus x to the 2 plus 1. Okay, now tell me, what can I write a little bit simpler than this? What?
Same equation as before.
It becomes what? This is x to the 4, yes? Because this negative sign under the influence of this even power will go away. Minus x to the 4 means minus x multiplied by minus x multiplied by minus x multiplied by minus x, so it becomes positive x4. So it becomes positive x4. And this next term, for the same reason, becomes 2x squared, and this becomes 1. You see, I changed something. But this change in x didn't affect the y value. The y value returned into its original position, into its original form. Whenever this happens, it means that jumping from a positive number x to a negative number x does not have any effect on the height of the point corresponding to that point. So this means that this is definitely symmetric with respect to the y-axis. Okay, so this part of the lesson is optional, but I want you to have a better understanding and things, not memorizing them. Okay, so let us, by the way, remember this function x to the 4 2x to the 2 plus 1. I will draw it with GeoGebra. Okay, so let us go here, take this away, and then draw the graph of the function to see if this is according to our predictions or not. Yes, I don't know, by the way, the shape of the graph, but I am completely sure. Oh, so that's not 2. Power 4 plus 2x to the power of 2, and then plus 1. Yes, so actually it is not a very strange shape. I was thinking that it would be a much better one. Okay, so do you think that this is a parabola?
Yes.
Okay, so the answer is no. Okay, and this is one of those cases that we cannot, because I told you that parabola has a property that at this level we haven't defined that. So might be there are two shapes very close together, but they are not parabolas. Remember, parabola is only quadratic equation. Sorry, I didn't hear you.
Can I guess like which part of the equation doesn't make it a parabola?
I don't know actually, but if you know the answer, I'm happy to hear that. So what
well,
you?
No, I'm not. But oh yeah, right. It's x to the power 4. Never mind.
Exactly. Because of x to the power of 4, this is not a parabola. Yes, that's what I'm saying. Parabola is only for quadratic polynomials. Don't let the shape of the graph fools you, because it might be not a parabola. How should I understand this is not a parabola? Because this is not a quadratic, it's a quadruple polynomial with power 4. If I take this x to the 4 away, then that's a parabola. But then you see that the prediction was still correct. This graph is symmetric with respect to the y-axis. Now let us make it a little bit more fun. This positive sign and this positive sign, let me change it to negative sign. Okay? Do you still predict that the graph is symmetric with respect to the y-axis or not? Think, yes or no?
I think no, because when you put minus, then minus times.
No, let us go back. Let us go back. Let me go back here. Sorry, I want to make sure that you understand what I mean. If instead of having this function, I have this function, x to the 4 minus 2x squared minus 1. If I draw the graph of this function, do you think that the graph is still symmetric with respect to the y-axis?
Never mind. It's symmetric. Sorry.
Exactly. Because if I change, so this you have a very nice recipe, even though it is not explained in the book, but I think you understand this is not higher than the level of your understanding. So if you interchange x with negative x everywhere in the function, and if that function turns out to be the original function, then it means that this function is definitely symmetric with respect to the y-axis. Okay? And hopefully you understand that this is the case, because if I change this to minus x, because of this power of 4, it becomes positive x4. If I change this to negative x, it becomes negative x to power 2. This part becomes positive x squared, but there is a negative, it becomes minus 2x to the 4, and finally minus 1. You see that is exactly the same function. So let me just do these changes there, okay? So here, let me just try to edit this. I hope that this time we might get a better function. We can play around with these concepts a little bit, so to see how this will go. Okay. Oops. Yeah. Now we have a more interesting graph, but you see, still everybody agrees with me that this is still symmetric with respect to the y-axis. Everybody agree with me?
Yes.
Yes, so even though the graph is totally different now, but our prediction and our understanding was completely right. Because it doesn't matter how complicated the function is. If I change x to minus x, nothing changes. It means that the function is definitely symmetric with respect to the y-axis. Okay, so this is a general idea. So this, now tell me, let us go back here. Is this function here, is this function also symmetric with respect to the y-axis? Definitely yes, because if I change x to minus x, nothing will change. Okay, so this behavior is very, very important to realize. Okay, and then we will see that all parabolas remain symmetric, but not exactly with respect to the y-axis, because you might see that you have a parabola here. It is still symmetric, yes, but not symmetric with respect to this y-axis. Symmetric with respect to a line, another line. For example, this line, which is called a line of symmetry. So if I ask you what is the line of symmetry of this graph, the y-axis plays the role of the line of symmetry. The line of symmetry is a line on which the graph on the left part of that is identical to what is the mirror image, not identical, is the mirror image of what is on the other side. So that is called the line of symmetry. So for example, let us explore this a little bit. So for example, let me give another quadratic polynomial. So let me get rid of these. So here, for example, let me write y is equal to x to the power of 2. This is this means that I am dealing with a parabola probably. And then let me write minus 2x and then I have plus 1. Yes. Well, let me just keep it like that. That was more interesting. Now you see what's happening. I have a quadratic polynomial x squared minus 2x, so definitely that is a parabola because it's a quadratic term. And then, do you think that this parabola has a minimum or a maximum? Just talk to me. Do you think that this parabola has a maximum or minimum? What?
I think it has a minimum.
It has a minimum. And what is the minimum value?
Zero.
No, what is the minimum value? What is the minimum value again?
One perhaps.
No, the minimum value. Do you
One.
No.
Okay.
What is the minimum value?
-1.
minus 1. The lowest height of the graph is the minimum value. Gustav answered where the minimum occurs. These are two different things, okay? So remember this function. Let me go to the bag analogy here. So what does it mean? Let me go to the previous page. Remember this function, x squared minus 2x. Oops, what did I did with this? Okay, no worries. Okay, let us go to the previous page now. So the function was this. Y equals to x squared minus 2x. This is not that trivial as these problems. You see, if I ask you what is the minimum value of this function, what does it mean? It means that you need to have a bag again corresponding to the output values of your function. And then you start putting all possible numbers to the x, and then you register the output somewhere in your bag. You throw it in your bag. Do you agree that answering the minimum value question for this function is much harder than the previous x squared function? Do you agree?
Yes.
Because, why? Because of this negative sign. If I increase the values of x, this value increases, this value increases, but I subtract them. We don't know what's happening. Which one will dominate at the end? Or this behavior remains the same for all values. Of course, I hope that you intuitively, this idea is clear for you. The growth of this is much higher, faster than the growth of this. For example, if I put 1, this becomes 1, this becomes 2. Here, this is bigger. If I put 2, this becomes 4, that's also 4. They are equal. But after 2, let us see what happens. If I put 3, this becomes 9, this becomes 6. If I put 4, this becomes 16, this becomes just 8. So you see, this is actually increasing. But if the values of x are small, between 0 and 1, the behavior is different. This starts decreasing. You see, if I give you 1 for x, x squared will bring you 1. But if I make it 0.1, x squared makes it 0.25, and if I give you 0.25, for example, x squared makes it, I don't know, 0.625 or something. Yes. Is the behavior correct or not? No, sorry, that was wrong. That was my. So let me don't confuse you. Let me write it here. I will clean it again. So if I put x1, x to the power of 2 is 1. If I start increasing the value of x, the values of x squared will increase. But if I limit myself between 0 and 1, the behavior of x squared will change. Yes. So if I put x equal to 0.5, x to the power of 2 becomes 0.5 to the power of 2, which is 0.25. This one is actually smaller than the original value that I started with. Okay, sorry, I made you a little bit confused here, but let me go back to the problem again. So I just wanted to mention that telling you the minimum value that will appear in your bag right now for this function is a little bit more complicated. It was not that clear that y minus 1 is the lowest value. It is not that hard to convince yourself that minus 1 is indeed in your bag. Okay, how should I do that? I put x equal to 1, and then what I get for y value is 1 to the 2 minus 2 times 1, which is minus 1. So definitely minus 1 is in my bag because it was attained for this value. But there is no guarantee that I have infinitely many numbers left. I put those numbers, I get all these numbers in my bag. Is there any easy way to understand why negative 1 is the lowest possible value? If I have GeoGebra available and I trust GeoGebra, this question is a primary question, is a very simple question. I want everyone understands that. By looking at this graph, if I ask you what is the minimum value, you should be immediately able to answer this. You should say minus 1. First tell me, do you have any problems understanding that minus 1 is the minimum value of this function?
No.
Okay, but now I can ask you another question. I can ask you when this minimum occurs. When this minimum occurs. This minimum occurs when x is equal
1.
to 1. So remember this question. When you are dealing with maximum and minimum, there are two types of questions that you need to differentiate them. They might ask you what is the maximum value, or they can just simply ask you what is the maximum of this function. Both of them are the same thing. They can ask you what is the minimum value or what is the minimum of this function. They can also ask another type of question. They can ask you to achieve the minimum, what should be the value of x? To achieve the maximum, what should be the value of x? They can ask you when minimum is attained, when the maximum is attained. Then they are asking about x value. If they talk about minimum and maximum values, they are talking about y value. So you need to answer that question by checking the y-x axis. And if they ask you when these maximum and minimum points are occurring or they are attained, then they are asking you about x values. Okay? And if they ask you about minimum or maximum points, they are asking you for both the x value and the y value. So for example here, this point, if I do this like this point is called the minimum. This point, let me make it a little bit bigger so that you can see that. Yes, this point that is bold now, this point is called the minimum point. When I ask you about the point, you have to tell me this point has x coordinate 1 and y coordinate -1. -1 is the minimum value. 1 is the place where the minimum occurs. So these are the terminologies you need to respect to. Okay, but this graph is very simple. But assume that you don't have the graph available. How can you convince yourself that the -1 is the minimum? This is the question. I want to go back and talk about this. And I want to have first to listen to your ideas about it. Do you have any idea how analytically I can convince you that the minimum value that you will get in this bag is definitely -1, not higher? This is what I want you to learn. This is part of the lesson, by the way. This is not extra material. I give you a hint. The hint is completing the square method somehow. It's not, by the way, the completing a square method, we learned it when we wanted to solve quadratic equations, yes? But now we want to use the same ideas, but for the quadratic function. I want to wait a little bit for you to see what do you say about it. Okay, let us do it together. Is it a complete square in this form, yes or no? This you can immediately answer. Is it a complete square pattern right now?
No.
So what does this lack from being a complete square?
C term.
Okay, C term. What is the suitable C term? Is it 10? Is it 5? What number is that? What is that?
0.
No, 0. If you say 0, this is not a complete square, is it?
1.
1, exactly. So this becomes equal to x squared. But when I write this, do you agree with me? Do you complain or are you happy?
Well, they're not equal to each
other. Exactly. When I write equal, I have to respect. So what can I do to make it equal?
Add the same thing on the other side.
There is no other side. I am going from one direction to the other direction. Remember, Rocco, this is not equation. In the equations, I can add to both sides. If I want to add This, of course, you can do this. You can write y plus 1 is equal to x squared minus 2x plus 1. But the point, this is correct. But the point is that I am not talking about y anymore. I am talking about y plus 1. I don't want to do that. I want to talk about the same y. Do you understand me? Okay, hopefully you understand me. So this is not what I mean. So there is another way. So what can I do to make this equality right, everyone? It's a crazy thing, but we can do that.
The only way I can come up with to take away the 1 is just put minus 1.
Exactly, yes, that's the idea. Yes, exactly. This seems like a silly way to do this, but this is not silly. First of all, now you understand that, first of all, is this equality correct or not? So I have added 1 unit and I have taken it away again. So you might say that, is Babak crazy to do this? No, there is a point for that. First of all, you agree with me that this equality is completely true. Why? Because 1 and 1 minus 1 are gone. What is left for me is exactly this one. But what is the point? Can you tell me what is the point?
Get a value for C.
Okay, so what happens for these things underlined?
They're the ABC values. And so you can use the ABC
Forget
values.
about ABC values. The reason,
Okay.
do you remember when I was talking, you might say that, okay, I myself know that this is quadratic equation. Don't confuse the concept of quadratic equations with quadratic polynomials. Okay, there is no equal 0 anywhere. Yes?
Okay.
So what is the pattern
Well,
now?
maybe it's you can put it into a function.
So what should I write for that? No, what was the reason? I want to make the complete square out of it. That was the reason that I added 1. So why do you forget about this?
Use the squaring pattern.
Yeah, exactly. So this becomes a square to power 2, and then I would write x minus 1. So what I have written here is this part, but now I have a minus 1 at the end. So I would write minus 1 here. Do you agree with me or not?
I agree.
Okay, so what does it mean? It means that everyone should agree with me. If you don't, please let me know so that I explain. What expression that you see here is a disguised form, is a different form of this expression. Whatever you want to say about this, you instead can say about this, and the other way around, because they are mathematically equal. So I hope that you haven't forgotten the point. What was the point? The point is that I want to claim that minus 1 is the minimum value in this bag. Now, is that clear for everyone? Minus 1 should be the minimum in this form, which was not easy to answer it in this form.
Yes.
So how? Can you describe it for me?
I'm thinking that the x minus 1, and that is proportional. No, what would you say? Symmetrical. And then minus 1 lowers the minimum value.
Not 100%. I am not very happy with this argument.
I'm sorry, Baba.
You're welcome. Let me give this guy a name. Let me call it capital X, yes? I want you to broaden your point of view. I have a capital X, and then if I stop here, if I just stop here with capital X squared, what is the minimum for Y? Everyone.
0?
That is 0 because that's the same function, the only difference is that instead of little x I have capital X. But now I have a minus 1 at the end. Can I ask you what is the minimum of Y right now in this form?
I guess it's -1.
It's -1, yes, that definitely. Because the lowest value that this can take on is 0. But y is not this one, is this one minus 1 unit. So it means that when it hits its minimum, which is 0, y takes on value 0 minus 1. So the minimum value of y is minus 1. Or in other words, x squared is always greater than or equal to 0. So x squared minus 1 is greater than or equal to minus 1. So this means that if I ask you what is the minimum value of this, you say that x squared minus 1 is a number greater than or equal to minus 1. So if I ask you what is the minimum is minus 1. And that is as simple as that. So the minimum of this function is minus 1. So the method of completing the square is actually very crucial. Yes?
That was my thought also.
Yeah. So that is something hopefully everyone understand that. So that is exactly, next session I will come up with all these arguments, make it very systematic for you. Don't be worried about that. I'm just giving you a lot of information. We are discovering something together. And then when everything is settled down, I will come back and review them and write them algorithmically. So after learning, at the end, you need to have it in your memory so that you can use it immediately, quickly. Okay? And quickly. So this is the minimum value of this function. So you learned a lot of things today. Some of them are very completely general. You learn. So by the way, I forgot to write the name parabola. So parabola. The graph of every quadratic function is called a parabola. Yes? Okay, so for example, let me go to this page. Let me ask you this question. Can you talk about the minimum? I want you to discover it analytically. Then we go to GeoGebra to check it. Okay, so for example, let me write this. Y equals to let me see, how can I do that? Okay, so x squared, I don't want to make trouble for you that much, 2x squared minus 3x, okay, and then I would write, now let me make it 6x, I don't want to make trouble that much, so 6x here, and then let me write it minus 4. Okay, first of all, do you think that there is a maximum for this function or a minimum? I want you to see that. Do you remember what I told you in the general case? Do you think that there should be a maximum or a minimum?
Yes.
Okay, which one? Maximum or minimum?
Minimum.
How do you know that? Do you remember? What was the criteria?
Because it's a negative. I don't know how to explain, but it's negative.
Yeah, exactly. So that is, whenever you have this number negative, you can compare it with this case, which we learned that it has a maximum. Whenever this number here is positive, then we will have a minimum. Yes, so our guess is that there should be a minimum. Okay, so let us calculate this minimum. I want to wait for you a little bit, but unfortunately in this way of recording, I do not have this option available to pause the video. Everything is much better, the quality and everything. I have lost the pausing option. Okay. Anyway, just talk to me. What do you want to do? I want to find the question is this. Y minimum, or sometimes people write it like this, or people write it like this. It doesn't matter, so you can write it in English as well. So let us write this. So let me write it here. What is the minimum of y? If you draw it by GeoGebra, you can immediately answer that, because it is not a very, you don't need to be very intelligent to see it. You just see what is the lowest level of the graph, and that is your minimum. But can you help me to do this?
You can start by trying to put in 0 for x.
No, this method does not work. How many? First of all, even if it works, that just might be a coincidence. How can I be sure that I cannot get lower values? This is, I want you to understand why we are making trouble for ourselves. There is a reason for that, unless we are crazy, yes? So you need to ask why we bother ourselves so much to convince ourselves that this is the case. Because you see, I want you to understand, I want you to feel it with your flesh and bones, yes? Why? Because there is no guarantee how many numbers are coming out of this function. There are infinitely many numbers popping out from this. Very strange numbers containing square roots, fractions, and whatever. Without spending so much time, I was hopefully, if I succeeded, I hopefully wanted to convince you that don't spend time. If your goal is to find the minimum in your bag, I found it in a matter of seconds. That minimum is -1. This is the power of mathematics. I hope that you appreciated what I told you here. Everyone, if not, please let me know, should be convinced that -1 is the lowest value that you get in this infinitely big bag of numbers. Okay, so let us go back here. What can I do?
You can try to do the same thing you did.
Okay, that is exactly what I am asking. Can you help me? What do you think? What do you think I will do?
Substitute value for x squared minus 6, and then you can see that perhaps -4 is the lowest.
No, so this perhaps is not good enough for mathematics.
Okay, it is the lowest value. How about that?
No, it is not. So how do you know that?
Okay.
So don't you understand what I'm saying? You repeated again the same thing after all these explanations. If you put 0 here, yes, you get, let me just repeat this for everyone. What is the answer is -4. This only tells you that -4 is in your back. Then what? Have you checked all other numbers? You cannot check all of them. There are infinitely many. How do you know that? By coincidence, by, I don't know, by accident. You cannot come up with another number which is lower than -4. Are you sure about that? This I want you to understand. The method that we want to describe is something that you are supposed to be sure about that. Okay, so what you gave me is that you told me that I put 0, I get -4. At most, I understand one thing. I understand that -4 is in my bag. That's it. That's the only conclusion that I can draw from this. Anyone else? You don't get my point probably. I don't know how to explain it anymore. Come on, are you living in my world now? What did we do here?
You completed the square.
So why don't you talk about that? So we want to complete the square. But unfortunately,
I don't see how we can.
no, okay, at least you can, okay, but that is very better to say that we want to complete a square, but I don't know. Because if you don't say anything about that, it means that you didn't understand anything. Okay, now you understand something. Okay, good. But let me ask, what do I need for making this a complete square? What is the number missing from this? Momentarily, don't look here. Can I turn this to a complete square by adding a suitable term to it?
Could you divide 6 by 2?
What?
Divide 6 by 2.
And square it. Yes, that's correct. 6 divided by 2 is 3 divided is 9. So I need to add 9 to it. So please do not look at this question. If I ask you, is this a squaring pattern, do you buy it or not?
by it.
Okay, so that's a squaring pattern. But the problem is that, is this the same expression? Unfortunately not. In the question, I had minus 4. I cannot just drop minus 4 and write positive 9 because I like to. Okay, unless, what should I do?
You compile it into the completing the square method. And then
No, before doing that. I don't know. Let me tell you something. Okay, so I want to answer the minimum, yes? Y is equal to x squared minus 6x minus 4. If I write equal to x squared minus 6 plus 9, do you agree with this?
No.
No. So do something that you agree.
Minus 13.
Yeah, exactly. Exactly. Minus 13. Yes?
Yes.
So it means that why on earth I chose to write minus 4 as 9 minus 13. I could write minus 4 infinitely many ways. I can write minus 4 to be minus 3 minus 1. I can write minus 4 to be minus 5 plus 1. Why I have chosen this very particular combination? Because in this case the first 3 becomes a complete square, which can be collected into a complete square, and minus 13, yes? And I ask you, what is the minimum value of this part? This part is greater than or equal to 0, only this part. So this means that the whole expression is greater than or equal to which number? Can you tell me?
Minus 13.
Minus 13. So this means that this y is equal up to here, but suddenly it is greater than or equal to minus 13. So it means that y is greater than or equal to minus 13. So this means that the minimum value of y is how much?
Minus 13.
So that is the answer. This is, you need to understand and learn. You need to be able to find the minimum value. Now, remember this function. For the last part of the lesson today, we will go to GeoGebra and check that if we have done everything right. X squared minus 6x minus 4. Yes? So let me get rid of that. Y equals to x to the 2, and then we go minus 6x, and then we go minus 4. Yes? Okay, so I need to zoom in so that we can see all the graph. So let us do this, and then this is the minimum. Unfortunately here it is not that clear. Let me see if I can play a trick so that number pops up. Yeah, so here, yeah, you see, this is the lowest value, and that prediction by calculation was correct. So hopefully, of course, I will repeat this more systematically next time, but hopefully you are understanding what is going on roughly, yes? Yeah, more or less. Is that right? Yeah, good.
Yeah, sort of.
Yeah.
100%.
Yeah, good. So it means that
60%.
So okay, 60. Yeah, I know it's a little bit hard concept, but yes, I will actually repeat a little bit tomorrow. And tomorrow I will be probably at the school because there would be no time, and that's a little bit unfortunate because I think for teaching mathematics probably this method is better. I can go back and forth between GeoGebra and the iPad screen, so it is very valuable. But unfortunately tomorrow I have to be in a school, and when I finish I do not have enough time to reach home for that. So I have to start your lesson there, and I will stream it on YouTube live, okay? So remember that, of course, you will have your Zoom open, so in case you have any questions. Yeah, that's a little bit unfortunate that this happens. I have to go only for one lesson to school, and then because I cannot have time to come back, I have to be there. Otherwise, I think, of course, I'd like to be in a school, but for this lesson, I think it was very illuminating when I go back and forth between GeoGebra and the iPad screen. Okay, so I think I can stop this video from recording here.